this is how you measure radioactive isotopes in a sugar battery, nuclear radioactive carbon-14 battery. First of all, we're going to show that I'm going to touch these two terminals. That's millivolts. It's 27. Radioactive, okay? And now we got two pieces of same length stainless steel, which that's also stainless steel, and sugar with pure H2O. There's no real true acidic solution that was added. It may make a little hydronium or some little bit of acid, we're not sure. May have impurities, but for the most part should be some portion of radioactive. This is how you tell the difference of radioactivity versus like not radioactivity. The only real difference is like acidic solution, and you should see that sugar water is not acidic. Sugar with pure H2O is not acidic. So not only that, we put these two test leads down to each of our panels, and we get very little millivolts. So not only that, wood is radioactive as well. Now here's how you show that wood is radioactive. Now basically okay, well, wood is radioactive, but it's not giving off much energy. So doesn't give off much energy. Very little. But a sugar battery, radioactive sugar battery, will give off this voltage right here at this size with this mixture. These proportions, millivolts, will be constant. It will never get less than that until all the radioactive isotopes finish decaying. Like, technically, radioactive decay may possibly be constant with a percentage of carbon-14. So, I mean, that's pretty much how they do certain biological radioactive carbon-14 dating. It has to radiate, or it has to be present, basically, I think. This is what I think. Pretty sure it has to go off some form of energy, or it has to have a specific mass in a mass spectrometer. So it has to be a certain density to that mass by volume. But essentially you should be able to say that constantly any radioactive isotope that radiates should be giving off a half-life, which means that whatever the half-life is half of that radioactive isotope will decay in that amount of time. Carbon is 5,000 some odd years. So if you have an ounce of carbon-14, then half of it will decay within at some point in 5,000 some odd years. And then what that means is that for each carbon-14, there is decay at the rate of half in that many years. So carbon-14 is constantly decaying. So if you have a whole bunch of it, it's constantly decaying, and then it means that it is always, carbon-14 is a percentage of carbon that's always radioactive, but it's a percent based on the total amount of carbon-14, and it decays constantly at half the half-life of 5,000 some odd years. So it's not necessarily predictable, but in this way, measuring the voltage of a source of low amounts of voltage in a source of carbon, like sugar here for instance, or an organic molecule, you're going to get a voltage like this. And these are neutral. This is a neutral substance for the most part. Basically, and that's stainless steel, which is highly resistive to the flow of current. So it was 27, 28 millivolts. That means that radioactive carbon-14 or whatever other isotopes might be in this sugar water are creating voltage. Other than that, you have like cell phone signals and stuff like that. And you know, your basic heat energy and stuff. Well, and then if there is anything in the sugar that's causing acid or bases, but sugar doesn't necessarily create an acid or a base. But basically, that's it. It's constantly half-lifing, but it's by the half of the dosage, which is not extremely abundant. So that's why the voltage is in millivolts. It's extremely low for like what I have here, like 3 pounds of sugar, compared to these steel terminals. So basically, it takes a lot of sugar and a lot of steel in water to increase the voltage, and essentially you get a battery like this. And basically, as you can see, there's no air voltage from this terminal, so it's not cell phone signals or heat. But when you put them up here like this, you get, hold on, you get 27 millivolts. So that's it. There it is. It's consistent. It won't reduce. It's constantly radiating carbon-14, which is all throughout the human body. It's in animals, it's in plants and biology. But its density, well, it's dense enough in humans to cause us to be radioactive. But that's pretty much it. How radioactivity of carbon 14 and a sugar battery is what this video is going to be called. Works.